Non-line-of-sight imaging, or imaging around corners, enables new capabilities in a wide range of applications, including autonomous vehicle navigation, remote sensing, and medical imaging. Recent approaches to solving this challenging problem employ optical time-of-flight imaging systems with highly sensitive time-resolved photodetectors and ultra-fast pulsed lasers. The sensor measures the time it takes for light from a laser pulse to propagate to a wall, around the corner to a hidden object, and back. Reflected photons from each object are captured by the sensor over time, and by scanning multiple locations on the wall, the 3D geometry of the hidden object can be recovered. However, widespread adoption of the technology remains a challenge because of the requirement for specialized, expensive hardware. Moreover, acquisition times for diffuse objects are very long due to the rapid signal falloff at increasing distances. We introduce acoustic non-line-of-sight imaging, in which modulated acoustic signals from a speaker propagate to a wall, reflect off a hidden object, and return to a microphone. By scanning or using an array of speakers and microphones, the 3D geometry of the hidden object can be recovered. Acoustic non-line-of-sight imaging is orders of magnitude less expensive than most optical systems and captures hidden 3D geometry at longer ranges with shorter acquisition times compared to optical methods. The key motivation of our work is that the reflection properties of walls are usually specular or mirror-like for acoustic waves, so they should reveal the hidden scene more easily than optical setups. We therefore modeled the wall as a mirror, which allows us to image a virtual line-of-sight volume beyond the wall. Unlike the optical case, however, there are no focusing optics for the acoustics, so we cannot directly measure an image of the virtual scene. Instead, we use an array of speakers and microphones. Each speaker emits a linear sweep in frequency, and each microphone captures delayed versions of the signal reflected off of the scene. Mixing the transmit and receive signals together produces peaks in the Fourier domain, corresponding to the distance of the scatterers. In practice, we observe specular scattering behavior off surfaces that are flat relative to the wavelength, and retroreflective-like scattering off of corner geometries larger than the wavelength. For scatterers smaller than the wavelength, diffraction of waves around the scatterer produces diffuse scattering profiles. We rely on the strong specular or retroreflective scattering components for our reconstruction, and, similar to Wi-Fi or radar-based imaging, we assume that the geometry of the hidden object reflects some specular signal back to the sensor array. For measurements taken at different spatial locations with closely spaced speakers and microphones, we can use efficient and closed-form solutions to reconstruct 3D geometry. This sampling arrangement is analogous to confocal sampling in optical non-line-of-sight imaging, where the laser and the sensor share an optical path. However, these confocal measurements represent only a subset of the general non-confocal case, where all microphone measurements are captured for each speaker location. We derive efficient reconstruction procedures for this case, which allows us to capture more of the signal returning from the hidden object. Our reconstruction procedures are inspired by seismic imaging methods, where shock waves are created by explosive charges on the surface, and displaced microphones capture the reflected waves to reconstruct underground surfaces. Computational algorithms estimate the response at the surface as if the shock wave and microphone were placed together at the midpoint location. Adapting these techniques for acoustic non-line-of-sight imaging allows us to apply efficient confocal reconstruction procedures to the full set of non-confocal measurements. We build a hardware prototype to evaluate our technique and scan a variety of scenes. The hardware prototype consists of 16 speakers and microphones mounted on a vertical bar, which is scanned horizontally with a translation stage. Each speaker emits an acoustic signal whose reflection is measured by the 16 omnidirectional measurement microphones. After scanning the array, we can reconstruct the 3D volume containing the hidden object. This captured scene shows the reconstructed shape of a cutout letter made of foam board for only the confocal measurements, for all the measurements, and with additional priors on the reconstructed volume. We position the letter around the corner at a distance of 2.2 meters from the acoustic array along the indirect path of propagation and angle the letter toward the direction of sound incident from the wall. This result reconstructs the relative position of 4 corner reflectors that are positioned around the corner from the acoustic array. Their corner geometry provides a strong retroreflective scattering response. Finally, we also compare the acoustic reconstruction with optical methods. In this scene, we place 2 cutout letters around the corner and scan them using our acoustic technique. We also compare to state-of-the-art optical scanning and reconstruction methods. Since the optical signal decays much more quickly with increasing distance, it is difficult to make out the more distant L letter located roughly a meter away from the wall, though the T shape can be seen at 50 centimeters distance. In the acoustic case, the T can be made out at 1.6 meters from the wall, and the L can also be made out. Moreover, the effective per-sample exposure time for the acoustic signal is roughly 100 times less than the optical signal. We hope that this new modality of acoustic non-line-of-sight imaging helps make seeing around corners more affordable and practical.